in Chinese, and I'm being called Xiaoxiong from my primary school, and today we need to beat Baby Bear by M31 using circle stack. And first I need to mention that why circle stack is important, because M31 is very efficient, because as they mentioned, this structure is very easy to implement in CPU, and the Baby Bear is also very efficient, but not as efficient as M31. So it may be 1.4 faster about M31. And the circle stack is based on M31. So you use the circle stack instead of the stack based on Baby Bear. You have 1.4 faster, and that's the point of circle stack. But you may ask why S2 is many times faster than Stone. Because Stone don't use Baby Bear. They use big field, and all these two are small fields. No, yeah. So the point of circle stack is M31 and is faster, and this faster, this optimization is strictly better. It's strict. That means in any case it will be better. Benius, how to?
IUS.
Yeah, and if you compare with the Benius may be more fast, but it can't do normal arithmetic. And the normal arithmetic will be not native in Benius. And in Vitalis' blog, he said the Benius the cost of Benius is its theoretical complexity. But I think it's not only the theoretical complexity. It may have some trade-off, because it is based on binary field. And the structure is not same as this field. So if you want to do some regular computation like this, is very native in this field, as well as your number is your number here is less than p about this. But if you calculate 1 plus 1 directly in binary field, it will be 0. So you will need to use some technique to figure out that, so the efficiency will not as much as the native computation in the binary field. So in some cases, the Benius will be faster, and in some cases, these two will be faster. So the optimization of Benius is a trade-off. It's not strict. But the M31, the circle stacks, the optimization is strictly better. And for example, in some cases, hash or AES, some symmetric encryption, you use binary Benius will definitely be better. Yes, but other computation, I'm not sure. It depends. And so I just to emphasize why this factor is enough for us to do research on circular size because it strips better. Okay, now what's the problem of M31? Because like a RISC-0, they use Babel, right? And we all know, they all know M31 is faster in CPU. But why they don't just use M31? It's because M31 it don't have a native group of a native smooth group. For example, for Babel, P equal to then F P, the multiplicative group is of size. So it's have a factor of 2 to 37 is a smooth field. Okay, so when you do FFT or FI, you need to halve the domain. You halve and half, and you divide and conquer. So you need a field that have a factor of 2 to n, and n is big. So for Babel pair, you have the multiplicative group of size. And for binary field, the additive group is just 2 to n. So you can do the additive FFT on the binary field. So it's also very efficient. But for M31, the P equal to 231, the additive group of size P is not smooth. It don't have a factor of 2 to n. And the multiplicative group is also not good, right? So how can you find a group or a subgroup of size of size 2 to the n or have a factor of 2 to the n? So you can extend the field, just Fp square. You know this is a finite field. All Fpn and P is a prime. All this is a finite field. So you can extend the Fp to Fp square. So and the additive group of size P square is also not smooth, but the multiplicative group of size P square minus 1 is equal to okay.
Yeah.
So you may have because you can divide P square minus 1 to these two, and P plus 1 is 2 to 31. So you may have a subgroup of 2 to 31. So in this group, you may can find some subgroup of 2 to 31. So you can use this subgroup or coset of that group to do the FFT. Okay, now you need to extend the Fp to Fp square. An easy way to extend it is just see it as a complex number, as well as P more 4 is 3. You can extend it as a complex number. Because first you have one number. Now fp squared, you have two numbers, x, y. So you need to define the operation on the pair instead of a number. So a natural way is like a complex number. So you just x. You just see the pair as the complex number. Then you extend the field. Right? So x, y. So x0, y0 plus x1, y1 equal to x0 and x0, y0 and x0, y1, x1, y0 is just the complex multiplication, right? Okay, then you extend the field. Now you have and in the multiplicative group of this complex number, there are p squared minus 1 elements. You need to divide them to p minus 1 class. And one class is the subgroup, and others a coset of that subgroup. So you need to divide to p minus 1 classes. So how to divide this p squared to minus 1 complex number? A natural way is to compute the norm of a complex number, right? Every complex number have a norm. So, for example, z equal to the norm is z is x squared, right? So we can find that because it's a multiplicative group. There are no 0, 0, right? So we can find that k for k 1, 2, p minus 1. For every k in 1, 2, minus 1, there are exactly p plus 1 solution. Yeah. Or there are p minus 1 complex number. Their norm is 1, is 2, is 3. So you use norm to evenly divide these elements in the multiplicative group. So then you need a subgroup. It's very easy because the subgroup have the unit element. Unit element is 1 minus 0i, right? Is unit element of multiplicative group. So is 1, 0. So 1, 0, so k equal to 1. Right? So for this equation, there are exactly p plus 1 solutions. So and they have the unit element. So it is a subgroup, and others others are cosets. So now you get a subgroup of size p plus 1. All its points are in this curve. So why we need this circle curve? Because this circle curve is a group, and the group is of size 2 to 31. That's why we need this. Okay. Now we have a subgroup of 2 to n. And what we need, we need use this subgroup or its coset to do the FFT. Okay. So in FFT, we need to halve the domain every step. So we need operation on the domain. Now the domain is all the points on this curve, or its cosets. Now we need some operation to halve the domain every time. And an easy way to halve the domain is the square. Yeah. In a cyclic group, for example, in normal FFT, the domain is 1 omega. It's like this, right? And when you square every element, then you get 1 square 4 8, and then you square to get 4. So you square the elements in the domain, then you half and half, right? Okay. So you can also do that in this domain, in this curve. But so you can define the square on this. It's just multiply itself, right? And it is pi xy. Just like this, x, and this is because we use this to reduce this to this. Okay. So this is the square in the curve. So you can use this operation to have the subgroup, or for example, Gn. We donate all the a subgroup of size 2 to n, because the curve have this. So for any n, you have this subgroup, right? So you can do the square operation on the subgroup, and it will half and half. But I want to add another operation. Is if jx is x minus y, it is an inversion. It's an inversion of the group. It also an involution. Inversion means in a group, the element multiply the inversion is unit element, and the involution is that j x y equal to x y. So the inversion is also an involution. So why we need an involution? Because we don't want to always deal with two number. It's very complicated. So if we use this operation to half the group or half the coset in the first step, then we will map x, y to x. Then we will have only one number. That's why we introduce the involution j. In the normal FFT, they don't need an involution because they just use square and half and half. And here we want, at the beginning, we have some pairs, but we don't want to deal with pairs. And for these pairs are the solution of this curve, right? For this pair, for every single x, there are two y, right? For every single x, there are two y, right? So our idea is that we can just half the domain to element the y, right? If we element the y, then exactly we half the domain. So we can just use the involution to half the domain. We map, so what we get is just Gn it's like this. It will map x, y, and x minus y to a single element. The element is the element of the quotient group, right? So you can write it as this. But all the information of this is x, right? Because it is on the curve. So we fix the x, we get this. So we can just pick the x. So if we use the involution on the domain, we will element the y. So it's very convenient in the next steps, right? But there's a problem. We need to ensure that the involution map is 2-to-1 map. You need to ensure that for every x, there are exactly two y. But if x is 1, there only one y, right? So you can't. So for every subgroup, we have unit element. So in every subgroup, the involution in every subgroup is not 2-to-1. So that's why we need a coset. We need that Q, right? We need Q. We cannot just remove the Q. Because if we remove the Q, the map is not 2-to-1 map. So now we need a subgroup and get a coset. It must be a coset. In the normal FFT, it can be a subgroup, it can be a coset. But in our case, it must be a coset because it is to ensure the involution is 2-to-1 map on the domain. And also, this is not enough because in this, they are in this domain, they don't include for any x, for some x in this domain, they don't have 2y in this. So we need to get this. You know?
So
Yeah.
I have a question. So
Yeah.
You're saying the J, right?
Yeah.
The J map is for 2 to 1 map.
Yeah.
Actually, so because we after one J map, the 2-dimension element will be a 1-dimension element.
Yeah.
So how can we do another J map
No,
to make
Well,
sure that
no more J.
No more no more J mapping.
Just once.
J, we just use J once.
So I think J is not for 2 to 1 map because J kind of we project the 2-dimension element
Yeah.
to X.
Yes,
X.
it's why we need J. But we need to ensure the J is 2 to 1 map because we need to use it in the FFT. It's not the reason, but we need the property.
I think the FFT is for because we have 2 maps, right? One is J,
Yeah,
the inversion map, and then another pi kind of a rotation map, right?
yeah.
I think rotation is kind of the map we used in FFT, so we can one after one, we can.
No, in the first step of FFT, we use J. Yeah.
Okay, and generally in FFT you don't have to use J because J is like the purpose of J kind of we map each 2-dimension element into 1-dimension element.
Yeah.
So we cannot do it twice, right?
Yeah.
So,
We can.
FFT is a recursive function.
Yeah.
Recursive operation. So if without the J, if we don't have J map, we can still build construct a FFT algorithm even without J.
Mm,
Right?
but how you do the first step of the FFT?
First step
Yeah.
FFT.
In the first step of FFT, we need to calculate the evaluations on the domain after the J map. So if you have the domain in the first step, you don't need to do extra computation or something. You just
So it's an optimization or it's a necessary step?
I don't know, but if the J is 2 to 1 map, you can look at it as a normal FFT step. Otherwise, you will do other things
So what
to solve this.
The next question is what's the correspondence in, for example, a multiplicative FFT? So is there a J equivalent in the traditional multiplicative FFT?
As well as it's a 2 to 1 map, you can just modify the original FFT and get done. But if it's not a 2 to 1 map, you cannot look at it as a FFT step. So you may figure out some other ideas to solve this, I think.
Okay.
Yeah, if you just maybe it's not convenient. So if you don't use J, you need to carry pairs all through the computation.
Yeah.
I think it may be also okay.
Maybe not necessary to use J.
Yeah, it's not necessary. So I say you use J to get only one map to only one element. So it's more convenient, I think.
Okay, yeah.
Yeah. So after j, we can just element
Get rid of the
get rid of the y. Yeah.
Yeah, okay.
Yeah. And also we need to ensure that j is 2 to 1 map. So we cannot just use the subgroup. We need to use the coset. And also to ensure the 2 to 1 map, the two elements x, y, one is in here, and one is in here. So we need this domain. Okay. So why the FFT domain is look like this? It looks weird, and I explain why it looks like this. It's necessary. Okay, okay, and there are some special this called twin coset. There's some special twin coset. It's like this. Yes. So this is unique for every n. So we can just use this special twin coset called standard position coset, and it can ensure the two property that j is 2 to 1 map, and also pi is 2 to 1 map. Pi is square. And the square is easy to say because you square this, and the square in the subgroup is 2 to 1 map. So you square this, you get pi this and pi this, and pi in the subgroup is 2 to 1 map, and the pi to the q is another q. So after the pi, the square, you also get it is also a 2 to 1 map, because in subgroup it's a 2 to 1 map, just like the normal FFT, because it's a cyclic group of two n sides. So now you have a domain look like this. Sometimes a special twin coset look like this, right? And this is the standard position coset. And for every n, there's a unique q to make this standard. It's just like what? Just like there's a cyclic group, right? It is the unit element, and this is it. And you need to rotate the subgroup to make it symmetric along the x-axis, just like this. For example, 1, 2, 3, 4. You rotate it to 1, 2, 3, 4 to make sure it's symmetric along the x. So it is unique, right? So that is standard position coset. So in this coset, you can use j in the first step to half the x, xy to x, and then use pi to square, and half, right? Okay, then you get the.
So after the J map, so we got the one dimension element x, right?
Yeah.
So how to do the square with the pi? So
Yeah. Good question. How? Okay. Now you use pi on the x. It is, remember, it is actually is the element of the quotient group, and the pi is x. It is it should look like this, right?
Yeah.
So you don't so you because you don't care about this, right? Because
Yeah,
yeah.
actually I don't care.
You don't care about this,
Yes.
so you just pick that,
I see.
right?
So you like in every step you're carrying the x and plus minus y, but you're only using x.
Yeah.
Okay.
Because you don't use the y to calculate the x. So you can just pick x.
So only in the end.
Hmm?
So should be only the end. So we have, for example, n minus 1 times pi maps. And then we use the pi x to, only in the end we map the, we take the x.
Yeah.
Instead of
If the graph in the paper is just like this, right? And in the end you can pi x, and also you can see, you can look at just in every step you can use pi x, because at the end you use pi x, it's easy to understand, but at the beginning you use pi x, it's easy to calculate. It's the same. Yeah. It's just like you just square, and at the end you get two elements, x and these two, right? And then you use j to map to x. Or you use JMap as the first step. You get x and then you pi x. Yeah, it's the same. So now you have a domain. You have a FFT domain. You have a domain of 2 to n. And also you have some operation j and pi to map to half the domain, 2 to 1 map and half. So then you can do FFT on the domain. Now we only construct the domain. So we now use FFT on it. So first, why we need FFT? Because we need to use Fry, right? First, we have some computation, and the computation have some trace or witness. We encode this trace, this witness, the intermediate of the computation, as the evaluation of a polynomial, right? There's domain D. And we let the trace equal to the some low degree polynomial. The evaluation on D. D is trace domain. Now we have the evaluation of the polynomial on the trace domain. Now we need to calculate the coefficient of the polynomial. So we use FFT to calculate the F. Why we need to calculate the coefficients? Because we need to evaluate. We need to evaluate the polynomial, the low degree polynomial, on another bigger domain called evaluation domain. That's what Freud do, right? You expand the trace using the low degree polynomial f. You evaluate it on a larger domain. So the evaluations is code words, right? So now what you need? You need a low degree polynomial. So you should first define a low degree polynomial on the curve. Right? Now it's not just a finite element, finite field element. It's two finite field elements. It's a pair. So you need to define a low degree polynomial on the curve, on the pair. So because you have two numbers, so it's bivariant, right? F, X, Y is bivariant, two variant, and you need a low degree polynomial, so you can constrain the total degree, the degree of F less just like this. But why n over 2 is because at the end the dimension is n plus 1. If you define n here, the dimension is 2n minus plus 1. It don't look good. So you define n over 2 here. So you limit the total degree. What's the total degree? X, A, Y, B. The total degree of this is A plus B. You just sum the degree of all variable. Okay, and but now you have some structure on the curve. Because you define the polynomial on the curve, and all the points on the curve satisfy this equation. So when you meet x squared plus y squared is 1. So it's equivalent that you just move this. You just move this, right? Because in the curve, x squared plus y squared minus 1 is 0. So it is equivalent to the mode. Mode is something is 0. Right? So this is the function domain of the FFT. Not FFT. It's what means by low degree polynomial on the curve. It's L, N, F, just like this. Right? It's
So x, y is a small f, right?
Yeah.
Small f. No, not big f.
not
Big, the capital F.
Oh.
Actually, kind of is extension.
Right,
of
this?
Circle size. There's a small f here.
small f equal, right?
Yeah.
Oh, this?
Small, not small f and xy.
Small f and xy.
Yes, small f and xy. Yeah, because Ln, the parameter in Ln actually means the exciting field. The capital F means exciting field. Capital F.
Capital F.
Such F, actually.
Yeah.
Yeah, so in the definition,
Oh.
we have to use small f.
But
Pronomial belong to L and F.
but f is a extension field, and this is a polynomial of the
Right,
that.
but I mean the definition.
and
It's okay.
it's okay. And the f is in it.
Okay. Oh,
Small f is in it,
I see.
right?
I see.
Yeah, small f is in it.
Yeah.
Yeah.
Small f. Okay. Yeah.
So that's what means low degree polynomial on the curve. We define the low degree polynomial. It's f here, and we now can give a basis of this space, or calculate the dimension. You can find that because s square plus y square equal to 1. So y square is 1 minus x square. So you can just substitute every y square to 1 minus x square. After you do that, you can write the f into right? Because every these things we just substitute this, right? So we element every big y's, right? So we only have this only one y here. So we can, this part and this part is independent because it don't have y and it have y. So we can write the basis of these two is 1x square x 2 n over 2, right? You can over the n over 2 and yx n over 2 minus 1, because this n over 2 minus 1 plus 1 is n over 2, right? So how many dimension is just n over 2 plus 1 plus n over 2, right?
Yeah.
So it's n plus 1. So the dimension of it, all the low degree polynomial is n minus 1, right? N plus 1, right? And n here is 2 to n. Because it's the size of your domain and the coset, your yes, and this looks not good, right? Because we need to half. We also in the FFT step, in every step, we half the domain. We also half the basis. We can recall what FFT do. FFT is you have some evaluation. You get F. Okay. So in the normal FFT, the basis is 1, omega 3, omega 4, this. Oh, no, it's the domain. It's the domain. In normal FFT, the basis is this, right? Okay, so you have some value. You have some evaluation. And you need to get the coefficient of the F. And what coefficient? Coefficient of a polynomial is about a basis, right? So in normal FFT, the basis of the FFT is monomials. It's like this. So every time in the FFT, in every step, you just divide and conquer. First, fx, you can divide the fx to f0x square plus x, right? Assume that you have some evaluation of this f. Now you can calculate the evaluation of this. Because f0x equal to fx equal to f minus f and 2. And f1x equal to fx minus f or 2x. So now you have in FFT, your input is the evaluations of the f. Now you transform this evaluations of f into some evaluations of f0 and f1, and use this evaluation of f0 and f1 as the input of the sub FFT. Then you call two sub FFT. In sub FFT, you calculate the coefficient of f0 and f1, then combine them to the coefficient of f, right? That is FFT. So use this formula, you can get the evaluation of f0 and f1 by f, by the evaluation of f. And this one give you the coefficient of what? Of this, right? But this one, this sub FFT give you the evaluation, give you the coefficient of this, right?
Yeah.
Right? Okay. So these two FFT exactly as a same FFT. These two have same size, so the algorithm is the same. So you divide a big problem into two same problem, but the input is not the same, right? So f, you can see the basis of f0 and f1 is what? Is 1 s squared x4 x, right? The basis of this is of the coefficient it's provided is of this basis, right? And this x shift the f1 to x, right? So the coefficient of every sub FFT is over this basis, right? And so we can write the basis in another form. We can write this one x 2 to n minus 1. We can rewrite it in a tensor form. And 1 x squared 1 x4, right? But here in this step, what is their two bases? It's just x, just 1x, a tensor. Tensor 1s squared, x4, x6, right? Because in every two sub-FFT, you give you the coefficient of this, and then you use x to shift this. And in the next step, in the next step, f0x equal to f00x plus x f01x, right? So you can write it as 0 s squared x squared f01 x 4, right? It is the same, and but when you use f0, you use x squared as input, so so I write x squared here, and use x squared in the formula. Okay. So how about this one? What the coefficient is provide? This sub-FFT. It provides the one because f0x, it provides the coefficient of 1 s squared, x4, x6, x8, right? It's what f0x provide. And what is f00 provide? It provides the coefficient of 1, x4, x8, and this one, right? So what this provides is 1, x4, x8, right? So then this also provide this, and use x squared to shift it to this. So how to calculate the coefficient of this? It just shift it just use the sub-FFT to calculate the coefficient of this, and use this tensor to combine, right? To combine them to the coefficient of this, and then you get the two sets of coefficient of this. Then you 1x to combine them to the coefficient of this. This is a normal FFT. So now we look at the FFT on the circle curve. First, First, in the surface curve, you don't know this. You don't know this, right? This is what we got in the first, but in the circle curve, we don't know this. But we can construct this using step by step, right? In the circle curve, the first step is this. Right? The first step is this. You get some evaluations of f, x, y. Then you can calculate the evaluation of f0, x, and f1, x. Then you use the sub FFT to get the coefficient of f0x and f1x and combine them to get the coefficient of fxy, right? Okay, so now we use this method to calculate the basis of FFT. First, I don't know what f0x and f1x, what's the basis of it. I don't know, but it's just assumed like this. And whatever it is, the basis of fxy is look like this, right? And because these two are two same sub-FFT with different input, so the basis of these two is the same. So when we get the coefficient of these two FFT over this basis, we use y to combine them to get the coefficient of fxy. So the basis should look like this. And this is the basis of the f0x FFT. And what is the basis of this? f0x is f00x square. No, not square. It's pi. It's a pi x. And pi x is this pi x. And it's just like this. Just use the square map. Just it's square map. It's also square map, but here the square map is just square. But here the square map is this. But actually it's the same. Okay, you have this. So in this step, you use x, 1x. The basis of this is 1x times something, right? This is the basis of this, right? Because you use the sub FFT to get some coefficient of f00 over some basis. Also, you use sub FFT on f01 to get some coefficient of some spaces, same spaces, and use x to combine them to get this basis. Okay, now how to calculate this? 0x is f000 pi x plus x f001 pi x, right? It's just like this. And you use pi x in the x, 00 pi x equal to f000 pi square x and plus pi x f001 pi square x, right? You just use x, you use pi x as x here, you get this. And you can just put this into this and into this, right? So what's the coefficient of this sub FFT get? What is, it's over another unknown basis. And F001 is also some unknown basis. And you use pi x to combine them. So it's 1 pi x times 3. So go along with this line. We can get the basis is just 1y tensor 1x and 1 pi x and tensor 1 pi square x and to the end. It is the basis. Maybe 1 pi n minus 1 square. Right. This is the basis. And the pi x here is like pi x square x is 2x square. It's like whatever it is. Yes. And now we get the FFT basis of the of what? Just the FFT basis of
FFT space.
Of the FFT space. And now this is the basis of the FFT space. Okay, so what's the dimension here? Its dimension is 2 multiplied 2 times 2 times 2 times 2 is 2 to n, right?
Yeah.
But the L, N, F, the degree, not the degree, the dimension is n. I write wrong. The dimension is n minus 1, and the FFT domain, the dimension of FFT domain is n. So this is the dimension gap. So so I will not explain the detail in it, but you can find which one miss. Which one miss? Because pi, you can say the degree of pi square x is 4, right? Pi x, the degree of pi x is 2. So pi n x, the degree is 2 to n minus 1. Pi x is 2. A degree is 2, like this, right? 2, 4, and then 8. Pi 3 is 8.
2 per n.
Right, it's like this. The dimension is this. The 3 is 8, and the 4 is
4 pi per n will be 2 per n.
all right. Is
In the last step,
2 to n minus 1.
you need to compute pi n minus 1 in that step.
Oh, all right. Yeah. It's 2 to the n, right?
No, it's correct.
Yeah, it's 2 to the n.
No, it will be 2 power n minus 1, but we are
Pi
calculating
minus
pi n
one.
minus 1. We are
The
calculating pi
last
n minus 1.
step
In
is
the other step. Yes, pi n minus 1.
Yeah.
So in the last you get 2 n minus 1.
Yeah.
The degree is this?
Yes.
Yes. And pi n minus 2, you just get this, and along the way you get the x 1. So the biggest degree of x is 2 to the n minus 1, right? So you don't have the degree of 2 to the n. So that's what we miss.
bigger.
So you just miss the highest degree of x. So you can just add a term into the base, like pi nx, right? And what is pi ns? In the paper is vanishing polynomial, right? And pi x is v2x. Pi square x is v3x, and x is v1x, right? It's like this. So why it is a vanishing polynomial? Because when you square and square and square on the domain, eventually you will get x. You will get one element or two elements. If you don't use the j, you just square and square, just like this. You will get this. And at the last step, you pick the x. You use pi x to pick the x, then you get x. And if your twin coset is symmetric, so it is standard position coset, then the x here is 0. So at the last step, you get 0 something. So what it mean? It means that you square, and then you get 0 in x. So it is vanishing polynomial. Because it is it's only for the standard position coset. It is a QGN. For this, you have x equal to 0. So this is the this pi x, pi square x, pi 3x is also the vanishing polynomial. So you then the FFT space, this basis span, we call it Ln prime f, right? And the dimension is n, and the gap is pi nx, and is v n minus 1x. This is the gap. So you can represent any polynomial in this f you can represent any f belong to Ln f equal to g minus lambda and v n minus 1. because you need another parameter, another coefficient for the dimension gap, v n minus 1. And G is in L prime. So in the IOP, you need the FFT, you need the polynomial is low degree. So the constraint is that it's low degree. But when you do in the Phi, you need the polynomial is low degree. But in the FFT, the domain is less. So in the IOP, the prover should send the number first, because you have a one-dimension freedom for the prover. So in the IOP, the prover should send the number first, and then the verifier will get the G equal to F minus lambda Vn, and the Vn, the vanishing polynomial is just like the vanishing polynomial in the normal space, and it can be calculated in log in O log n. And here you can just calculate this in On, right? On is log for the space, and so the verifier can calculate the vanishing polynomial fast, just like this, and then they do the FFT on the G, because G is in the FFT space, right? FFT domain. Okay. Until now, we have the low degree polynomial, and we can do the FFT on the coset, and also it is also a proof that why this FFT is correct. And okay, that's all. Yes, to this.
Understand?
So you mentioned that you partition, in first you partition the whole group into according to the norm.
Yeah.
To the one to the p minus 1. Is it guaranteed that each partition is of equal size? So you get something
yeah,
like
I don't prove that. I don't. It's true. Yeah, you can prove it. My talk is not precise. I just give you some intuition.
So which means like x squared equals 2 has solution in the field.
Oh, S square. This equation over Fn, Fp over Fp, and xy is Fp. So and all the computation mod P. So there are some solution x y belong to F P square. There are P plus 1 solution in Fp square, and we define the operation on Fp square. We get Fp square.
So I mean, if you scale all the solution by factor of 2, then which corresponds to a solution of norm equals 4, right?
Yes.
And my question is, if you want a solution for the norm is 2, you need a scale factor which is square root of 2. And square root of 2 in the field. You need square root of 2 exists in this field. field.
Yes, it exists.